Sir, countability axiom, sir.
Means both means first there are two axioms, right? One is first countable and second countable. So
Only first countable.
Sir, sir started, but not in detail, sir.
okay. Means you
Just
know that.
definition. Yeah.
Okay. Means you know the definitions of first countable, but
Yes.
he did not define anything on second countable, right? So,
Yes.
So, so are you familiar with that basis kind of things? Means basis of topology?
Yes, sir.
Okay. And what about that RL, RK, and all those lower limit topology?
Sir,
No. Okay.
No,
See,
sir.
so today at the beginning we will discuss the problems which are left for you in your notes one, class notes one. Means I think that was covered in your last semester, and then we will see those kind of topology examples, means RK, RL, and then the topology generated by some sets A comma infinity and so on. Okay. So we will first start with that exercises. Okay. So let me off the video. Do you have that book by L.A. Prentice? You can open it by open it, or I'll write the questions also. So your first question was that x equal to r x equal to r and a topology tau defined on x where A belongs to tau if for each x belongs to A there exists an epsilon greater than 0 and a countable set B such that x minus epsilon comma x plus epsilon minus is B subset of A. So your x is this one R and tau with a collection of all such A such that for if you take an element A from A, then there is some epsilon and some B, means this B and this epsilon depends on the point X. Okay, such that this open neighborhood x minus epsilon comma x plus epsilon, this neighborhood minus B, it is subset of A. So now we are taking that collection. Your first question is whether tau is a topology. So is it a topology? Anyone?
Yes, sir.
Yes. So it's very easy to see, right? So this is a topology anyway, means you can check that X and empty set are already there. And for any set, if you consider U alpha a collection of elements from T, from tau, and if you consider their union over alpha U alpha, and if you take some X, then this X will be in some U alpha, and from this, from the property of U alpha, you can say that you can find such epsilon and beta. Okay, and similarly for finite intersection, you can take two sets U1 and U2 from tau, and if you take an element from intersection, you can similarly find out two elements R1, R2 and some B1 and B2, and which will give you the required B and R. Okay. The second problem was, so whether 0 belongs to 0, 1 closure with respect to this topology. So what is your opinion here? That whether 0 is in there or not? Anyone? Actually, this is not like teaching or giving solutions. Like your professor will teach you something in the class. He will also left something in the during his lectures, and in these sessions, means in the tutorial session, we just discuss about those. Okay, so means if I solve everything, then it will not be helpful for you. If you know something, you can tell me, and by this I also learn something which I don't know. Okay, so if anyone solved, or if you know how to approach, you can proceed. Yes, Navin.
So take x is equal to 0, epsilon neighborhood of 0.
Yes, yes. Just take the epsilon neighborhood of 0 and then. Okay, so minus epsilon, comma, plus epsilon. And then you can take your B to be the set Q, right? And then this minus or Q intersection 0, 1, and this minus B will be contained in, sorry. See, this will itself a neighborhood of 0, right? Now you take sorry, not in this way. Take U a neighborhood of 0. Then what we have to prove is that we have to prove U intersection 0, 1 is non-empty, right? Now since U is a neighborhood of 0, then by definition, so there will be some R, means the some epsilon, epsilon, and some countable set, say B, which will be contained in U. Now if we look at this one, then this is definitely contains at least one element from this set, right? Because we have just removed a countable number of points from this interval, and this set contains uncountably many points, right? So this implies 0 belongs to the closure. Okay. So there was one more, means the third one, that there is no sequence means there does not exist a sequence xn such that limit xn equal to 0. So there is no xn such that this xn equal to 0. Why it is so? Because if you consider, yes,
Sir, consider B as a sequence.
yes, consider B as a sequence, and then B is the sequence xn, and then if you consider this one, means minus 1, 1, it is as a neighbor minus this B, it will be a neighborhood of 0, right? 0 in tau, 0 in tau, right? So this contains no point of a sequence. Okay. So what was the second problem? Second problem was problem number 5, right? So what was that? So means if x comma tau be the topological space, And then O, if O is in tau, means if O is an open set, then this O will be contained in A intersection O its closure. Okay, where A is a dense subset. Okay, so means you have a topological space X, and A is a subset of X, which is dense in X. Dense means A closure equal to, sorry, A closure equal to X. And then you can say for any open set O, means any element of tau, O is contained in A intersection O and its closure. Okay, so how do you proceed for this?
X belongs.
Yes, X belongs to O. Then can you please speak loudly? I can't hear you.
Then there exists an open set V.
Huh?
O is open.
Yes, then
A is dense, so V intersection A intersection O not.
yes, V intersection. This is the trick, like V intersection A intersection O will be non-empty, right? And this will provide us the result that this X is in actually the closure of A intersection O. Okay, so and in fact, what question further asked that in fact you can replace this set A for any open subset. Sorry, what was the second part of the question? Yes, like in fact, if A is not dense, in fact, if A and O both are in tau, sorry, not both. If A is in tau and B is any subset of X, then A intersection B closure is contained in A intersection B its closure. Okay, it is very simple and the approach is same as previous. Okay, and I left it for you. Okay, so the next problem is when in any Hausdorff space, first one was 7, any Hausdorff space, the finite sets are closed. So why it is so? Because Hausdorff spaces are T1 space, right? Do you know what T1 space is?
Yes, sir.
Yes. So every singleton set is closed. So since it is T1, so we can say it is in a Hausdorff space, every singleton set is closed. So it was fairly very easy. And then there was the second part of the question that every sequence has a unique limit in a Hausdorff space. And this was discussed in class, right? In a Hausdorff space, every sequence has a unique limit in any Hausdorff topological space.
Sir, Hausdorff spaces are T2 spaces.
Yes, we can. Yes, or Hausdorff T2 are same, right? So the definition is for any x comma y belongs to x. If x not equal to y, then you can separate these 2 points in terms of open sets. Means then there exists.
It exists two open sets Vx and Vy.
Yes.
Such that Vx intersection Vy is empty.
Yes. And where x is in say Vx, yes, y is in Vy. You have to mention this one. Okay, so once you said Vx and Vy, then in this case Vx and Vy means that V with index x and V with index y. But you have to mention clearly that x is in Vx or Vx containing x. Okay, in this way. So then the next problem was question number 8. It says for a function in a discrete, if we have a function, it is also very easy. Means in a function with discrete topology. Means question number 8, that f from x to y, where y with discrete topology. Then this f is always continuous, right? Whatever, oh sorry. Yeah, sorry. If not x, it should be x, right? If x is discrete topology, then any function and whatever topology given in y may be, then this function is always continuous, right? Now, what about if your space like x with indiscrete, means if x with tau, then tau consists of only empty set and x, and y with a Hausdorff topological space. Then what can you say about the function if f is continuous? Now, okay. Now, assume that f is continuous, okay. Then what can you say about the function f? About its range? What is fx then? Yes?
Singleton.
Fx is a singleton set. Fx is a singleton set. Okay. Then we will move to the problem. Yes. Problem number 9 now. Okay. Now you consider f and g are two functions from x comma tau to y comma tau 1, suppose, okay, and where tau 1 is Hausdorff, or x y comma tau 1 is Hausdorff. Then now consider, now assume that fx equal to gx, okay, not like that, it is for a dense subset. Now let a subset of x such that a closer equal to x, means a is dense in x, and f of x equal to g of x for all x belongs to a. Okay, then prove that fx is actually gx, means for all x belongs to x. Okay, means the function itself, means this, then these two functions are same. So what does it say? If we have two functions from a topological space x to a Hausdorff space y, and if they agree at a in a dense subset, then these two functions has to be same. So if you can remember, it was done in the class that if we consider a space A, sorry, if we like other way, if we consider a space B when see if we have the same assumption here, and then the set, if we consider the set x belongs to x such that fx equal to gx, then what can you say about this set? It's a closed subset, right? Yes. And therefore, what we can say is that since B is a closed subset and for each element x in A, we have fx equal to gx, we can say A subset of B, right? So if we take the closure, they will also have this property, but A closure is equal to x. So x contained in B closure, but B is closed, so this is equal to B. So this implies x equal to B, means f and g means this is actually your x. So fx equal to gx for all x belongs to x. Okay. That was problem 9. Problem 10 is problem 11 is very easy, but there is something to do with problem number 13. Okay. So what does 13 says? Union of nowhere dense set is, finite union of nowhere dense set is nowhere dense. Okay. So it is enough to consider two nowhere dense set A and B are nowhere dense. So what is the definition of nowhere dense set?
Interior of A.
Interior of A, then
Interior of closure of A is equal to
yes,
5.
this is equal to 5. Then what more you can say about this? Do you know that A interior complement is equal to A complement closure?
Yes, sir.
Yes. Then from here, what can we say? If we apply this one, then it will be A closure, its complement,
Complement closure.
and then closure is equal to
X.
y or x. X.
Or
Yes,
or
exactly. X. And therefore we can say A complement, is it complement? A closure complement is dense in X, right? Is it?
yes, sir.
This is A closure complement. A closure and then its complement is dense. So a set A is nowhere dense. This is an equivalent definition that a set A subset of X, where X is a topological space, is nowhere dense if A closure complement is dense. Okay, is dense in X. Okay, so now we proceed with this problem, that finite union of nowhere dense set is again nowhere dense. So for that, it is enough to consider two nowhere dense sets. Right? Suppose A1 and A2 be two nowhere dense set. Right. So what you have to prove is that
A intersection is
yes, A1 union A2, its closure, its interior is empty, right? This is by your first definition, means by this one. Okay, so what can we say about this? But initially we don't know this one, so let us start with this one. So this is same as A1 closure union A2 closure, its interior, right? So what is that? This is same as A1 closure union A2 closure, and then by this one, this same as It's complement and then closure, right? First complement and then closure. So now this is same as A1 closure complement intersection A2 closure complement and its
Closer.
closure. Huh. Now what is A1 closure complement? What it is? Oh. Oh, sorry. We don't know. We don't know at this moment, right? Okay, let us apply one more result. So this is subset of A1 closure complement and its bar intersection A2 closure complement and its closure. Now you are fine. Now, what is this one? It is X. Hey, we still have one complement outside, right?
Yes, sir.
Yes, we still have one complement outside. Here is
5.
one complement. This complement. So this is X. Oh, sorry, this is intersection X. Its complement is equal to 5. So we are done. Means interior of A1 union A2 closure is equal to 5. Therefore, A1 union A2 is also nowhere dense. Right? So we have proved it for two sets A1 and A2. Now you can apply induction hypothesis to get for finitely many elements. Like similarly, what you do for the term for the finite intersection in the case of in the definition of topology, what you do for finite intersection, you just take two elements from tau and then prove that their intersection is in tau. Sorry. Okay. So in this way, now the next one asked whether we can whether we can take the countable union here. So whether the countable union of no-hair dense set is no-hair dense. Okay. So is it true that countable union of?
No, sir.
So can you give an example?
Sir,
Yes.
R with
Right.
usual topology, and we take singleton set Q from rational number, and union is is
Okay, so you take R with usual topology,
topology,
and you take
singleton set from rational number.
say AR a singleton set R, where R belongs to Q, right?
Okay. Yes.
Now, if you take the union of AR, it will be Q, which is dense in since Q closer equal to R. Okay. So there is one more problem, but I'll leave it for the moment because it's already 45 minutes. So I want to define what is so-called basis of a topology. Okay. Maybe sir will teach you sometimes later when you will learn something called second countability. But to define some interesting topological spaces which are defined on R, we need that concept. So that is why it is just a definition. For the moment, I will give you, and then we will see the examples. So suppose this is the basis. So let us start with a set. Let X be a set. Then we say a basis for a topology on X is a collection B of subsets of X such that what? Number 1, for each x belongs to x, there exists some b belongs to script b such that x belongs to b anyway. And the second condition is if b1 and b2 are two elements from script b and x belongs to their intersection, means b1 intersection b2, then there exists another element b3 belongs to script b such that x belongs to b3, which is contained in b1 intersection b2. Okay, so this is a subcollection of the, means a collection of subsets or a or subsets of the power set of x which has these two properties. Then we call beta to be a basis. So far we have not defined anything, we have not said anything about the topology. Okay, so now, so a topology generated by B. So how do we define? How? So a set U subset of X is open. Is open in X, or if we consider it as tau, then U will be, in other words, U will be in tau if for each x belongs to U, there exists some B belongs to script B such that X belongs to B subset of U. This is not N, it is X, okay? Be careful. So this is the definition of topology generated by a basis. Okay, so is it clear?
Can you give some examples?
Yes, yes, of course. Of course, we will have some example. Without example, topology is nothing, right? So without example, we cannot get anything. The very first example, consider R, okay, and take the subset B as is AB. So what is it? A comma B. What is this one? It's open interval, right? It's open interval. I am taking the collection of all open intervals, means all connected open intervals. Okay, fine. Right. Now you take, now you give the, now you generate a topology with respect to this basis. So what will be the open sets there? Suppose tau be the topology on R generated by script B. Okay, so then now if U belongs to tau, by definition, what it will be? U belongs to tau means there exists some element, say B from, sorry, yes, U belongs to tau means by definition
For each x.
yes, for each x, if we take x belongs to U, there will be some A comma B, right? Some open sets A B such that x belongs to A comma B subset of U. So can you remember? So can you remember what kind of open sets are those? Can you remember R with usual topology? What are the open sets there?
Open intervals.
Yes.
Intervals.
Open, not open intervals, man. In R with usual topology, not all open means open in not open intervals. They are arbitrary union and they are finite intersections. I mean, can we say that it's an open interval like 1, 2 and union 3, 4? This is open set in R usual, right?
Yes,
Is
sir.
it open? Is it open in R usual topology?
Yes, sir.
Yes. So is it an interval?
No.
No.
That's why. That's why this is this in this case the script B is strictly contained in tau, where tau we define by tau we mean the usual topology on R. Okay. So what we get is that this set B, this set means the collection of all open intervals of the form A comma B is a basis for the topology, for the usual topology on R. You can also, and your exercise for you, you can also find another one, means you can also get one strictly one proper subcollection of the script B, which will form a basis. So what are those? A comma B.
Open interval AB where AB belongs to Q.
Yes, A comma B belongs to Q. So even if you consider this collection, then this will also be a basis of R with usual topology. Okay. Now here I want to make one comment. You will remember when you study that second countability. This one is a basis, right? And how many such collections are there? Means what is the cardinality of this B1? It is countable, right? Yes, it is countable, right? So you will study in your second countability that a topological space is second countable if it has a countable basis. That's all. This is the definition of second countability. Okay, so you will learn all those when sir teach you in your class. Okay, but now you can just read this definition and forget for the moment. Okay, we don't need the second countability at this moment. Okay, is it fine? Now let's go to example 2. Example 2 of basis and subbasis. Suppose X is equal to R and we consider the collection of A comma B, where A, this side in left it is closed and in right it is open, such that A comma B belongs to R. Okay, you consider this as you consider this collection, and by this collection you generate a topology. Now generate a topology by this B. Okay, and this topology will be called RL, the lower limit topology on R. And this is very important to give something, to give some types of counter examples. Okay. Do you have any classes? Can I take 10 more minutes?
Yes, sir.
Do you have any classes?
No, sir. You
Okay,
can
okay. I'll just give 2 more examples and then stop here. Okay, so now this is your exercise to. Okay, it's fine, right? I just given you the basis elements. You can just generate a topology by the definition, and this topology will be called RL, means topology generated where the basis elements are A comma B. Well, in the left side it is open, so it is closed, and the right side it is open. In example 3, again we take X to be R. Okay. X to be R. Now consider the subset K to be 1 by n such that n belongs to n. Clear? Now consider two collections. One is B1, which is same as the previous A comma B, such that A comma B belongs to R and A less than B. And second one, you consider these collections A comma B minus K, such that A comma B belongs to R, where A is strictly less than. Oh, our class is supposed to continue till 4:15, right? I forgot.
Yes.
I thought it has started from 3. Okay, then it is fine.
Yes.
Maybe I'll finish by 50 minutes. Okay, so is it fine? I have taken two collections. Now take B to B, instead of script B1 union script B2. Okay, so now look at this collection. This B1 is same as the collection of usual topology, right? This one. I am adding some more elements in this set, which are of the form A comma B minus K. Now look at this kind of sets. If B less than 0, then what is A comma B minus K? B is strictly less than 0 or suppose less than equal. It is same as A comma B, right?
Yes, sir.
Yes. And if A is greater than 1, then also A comma B minus K is same as A comma B. So the effect of this operation means if we consider A comma B minus K, the effect of this one will be only on the open sets of only on the elements of the form A comma B, where 0 less than A less than B, I consider it as, and less than 1. So if we consider, less than equal to 1. If we consider A and B from this space, if we consider any one of A or B from this interval, then the effect of K will be observed. Okay. Now, if we consider tau a topology generated by this script B, then this topology will be called K topology. K topology on R. Okay. And we denote this K topology by RK. Okay. So we have RL, this is RL, and this is RK. These two are very important. These two is going to be very important for giving some counter examples or giving some examples of something. Means you will learn some whenever you will learn some new things like some Lindelof kind of things, normal topologies, normal or regular, and all those, and then these two topologies will be used to give counter examples or examples. Okay. We're going to be more details. So, any questions from here?
Sir,
Yes.
sir, please explain again the range of A and B. How have you written 0?
Yes. Yes. Sure. This one, right?
Yes, sir.
Now, suppose you consider. So one thing is whenever take. So what are the elements of this basis B? Script B. Okay. So this script B contains, first of all the elements of this type. Means whenever we have two elements A comma B. So okay, what I have described so far that A B whenever say in outside of this interval it is clear, right? Now what happens if we have something, suppose it is not 1/3. Yes, suppose it is 1/3 comma 1. Okay, we are taking this kind of things. So in this case, the basis B will contain this one and union with this. This will contain this one and this one also. So 1/3 comma 1 minus k. So what it is? It is 1/3 comma 1 minus this 1/2, right? Only the point half is in this interval, right?
Yes, sir.
Yes. See, 1/3 comma 1 minus k, this set and this set are same. So in this basis, both of the sets will be appeared in this one and this one. I'm taking just an example, and if more generally, if we consider an epsilon 0 less than epsilon less than equal to 1, then epsilon, and if we consider delta comma epsilon from here, and also of course for giving interval we define delta greater than suppose epsilon. Then this basis element means this B, then delta comma epsilon as well as delta comma epsilon minus this set. Both are in script B. Okay. So is it clear? Or still you have doubt? Sita?
Sir, if we take -1 to 1 interval in this case
Yes, of
also-
course. If we consider -1 comma 1 interval, then B will contain -1 comma 1 and -1 comma 1 minus k. Right? That's all. Means look at this one. So this B is the union of these two. It will contain A comma B, means it will contain -1 comma 1 and it will contain A comma B minus k. This -1 comma 1 minus k. Okay. Both type of sets. Is it clear now? Or you are still confused? So
Sir, actually, I am asking how you found this range. Like we
Oh.
have only one bound for A, that A should be greater than 1.
see, actually this k is fixed, right? This k is 1 by n whenever n belongs to n. So and this k is actually subset of 0 comma 1, right?
Yes, sir.
Yes. That is why when you apply this AB minus k, whenever A and B are outside of k, whenever one of them means whenever this A comma B intersection 0 comma 1 is empty, then you have no problem. In this case, only open sets of the form, open set of this type will be in the basis, means interval of this type.
Yes, sir. Now
But yes, but if it is not, if it is non-empty, then this set will contain some elements from here. In that case, we will consider two type of elements in the basis. One is this type, another one is a comma b minus k, this type. In fact, it is not this one, it is this intersection k, because taking this only. Okay. The next example is what? Consider again x equal to r and consider b to be the collection a comma infinity where a belongs to r. This will also form a topology. Okay, there is no standard name for this topology, I guess. So just leave keep it in mind that this forms topology when your bases are in of this type. Even you can replace this a comma infinity by minus infinity comma a as well. A belongs to R. Okay. Anyway, now you can take again R2. Just one last example for this type of basis. If you consider R2, now you take all circular disks. Okay. And take B to be the collection of all open circular disks. Then this will give you, then this will form a basis, because what it is, because if we consider any element x from R2, then of course any from a for a point you will get this one, right? In R2. You will get a circular region, or you can consider this b x comma 1 is the unit ball. And for the second condition, if you consider two circular disks, and if you consider the one point from the intersection, then again you can find out one circular disk in the intersection, right? So this, if this is your b1, if this is your b1, if this is your b2, then this one will be your b3. Okay. So now one more comment, that you all know that this one is fast countable, right? R with usual basis is fast countable, right? Is fast countable. You can also prove that this RL, this one, which is lower limit topology, let me write. This one, this is also fast countable. And this one, RK, this is also fast countable. Okay. And this is, if yes, this also again is going to be fast countable, it's no problem. Okay. So any problem, any question from this? Yes, no? Anyone? If you have any question, please ask. Otherwise, we'll stop here.